Hey, hello Physical Science, this is Mr. B, and today we are going to start our last section of Chapter 12. The title of this section is Universal Forces. So what's going to focus on in this section is forces that exist throughout our entire universe that act on kind of a much larger scale than the forces we've talked about. So remember, up to this point we've talked about a force such as like friction, or different types of friction, and gravity, and how they can kind of play a role with determining momentum, mass, acceleration, things like that, weight. But now we're going to kind of focus on forces on a much larger scale that exist pretty much everywhere throughout our universe. So to start, for our example here, it says this is an artist's depiction of the planet's surface, and it shows a world very different from Earth. So this is what Earth looked like early on in its formation, and then it says certain universal forces are present. So what that means is that there had to be some forces at work here that changed, or that helped change Earth's surface from that depiction to what we have today. Because when we walk outside onto our front porch every morning, that's not what we see when we look outside. So there are some forces that are present that were acting upon our Earth and the rest of our universe to kind of help shape and change the way that our planet looks. So some observations of planets, stars, and galaxies strongly suggest that there are four universal forces that exist throughout the universe. They are electromagnetic, strong nuclear, weak nuclear, and gravitational. So these are all the forces that exist everywhere throughout the universe that are kind of, four of the main ones that kind of help to shape, again, why Earth looks that way, and probably why other places in the world look the way that they are, in the universe look the way they do as well. So just some general information about a universal force. They can act over a distance between, our universal forces act over a distance between particles of matter. So what that means is that the particles don't need to be in contact for these forces to act upon each other. And then force is affected by the distance between particles. So if two particles are closer together, the force is going to be greater. If they're more farther apart, the forces are going to be weak. However, sometimes two things can still be acting upon one another, and their distance can be extremely far away. It doesn't really matter. So it's stronger, the forces, if the particles are closer together. However, there are some forces where distance isn't really a factor in determining whether or not the forces are actually going to be present between the two particles. So there are forces that can attract and repel on our list. So the electric force and magnetic force are the only forces that can both attract and repel. So the electric and magnetic forces are two different aspects of the electromagnetic force. So a big stretch there. Electric and magnetic make up the electromagnetic, and they are going to be associated with charged particles. So a charged particle could be like an electron or something like that, or magnets. Hopefully we know how magnets work, but we'll explain that with like a compass and things like that here in a second. And so electric forces act between charged objects or particles, and objects with opposite charges attract one another, and objects with like charges repel one another. So we've already talked about that. Clothes, we've all experienced this in our life, often acquire an electric charge in the dryer, and clothes that develop an opposite charge will tend to cling together. So that is why, again, the universal force of electromagnetism is actually acting on your clothes after you take them out of the dryer. So the reason why those clothes stick together is because they have opposite charges of one another. So again, universal force is present when you do your laundry. So that's awesome to think about. And then magnetic forces, they can act on certain metals, the poles of magnets, and moving charges. And a magnet, they have two poles, a north and south, and two poles that are opposite will attract each other, and two poles that are alike will repel each other. And that's kind of how a compass works. They have magnets that are kind of point to the north and south pole, and again, has to deal with different ways that they are attracting and repelling one another. And then a magnetic force of attraction holds the two train cars together. So these two train cars have opposite magnetic poles, and that is the reason why they are being held together and not repelling one another. And if you've ever tried to push two magnets together that are of the same pole, you're going to feel that they are going to repel one another. They will not stick together. You can actually feel the repulsion occurring there. So that's our electromagnetic force. And so now there's forces that hold the nucleus together. So two forces, the strong nuclear force and the weak nuclear force, act within the nucleus to hold it together. So remember, the nucleus of an atom has protons and neutrons in there, and then the electrons around the outside. So the strong nuclear force overcomes the electric force of repulsion that acts among the protons in the nucleus. So remember, protons are all positively charged. So if you think about it, well, why aren't all those positive charges repelling one another? And that's because there's something called the strong nuclear force. So that strong nuclear force is just how it says. It's very strong, and it is going to keep all those protons together. It's going to keep them from bouncing off one another. And then the weak nuclear force is involved in certain types of radioactive processes. So the strong nuclear force, just some more, is a powerful force of attraction that acts only on the neutrons and protons in the nucleus. So it acts over a very short distance, approximately the diameter of a proton, which you would expect because that's all it's acting upon, is holding the protons together. And it is 100 times stronger than the electric force of repulsion at these distances. So with two protons close together, there is a force that's constantly pushing them apart, saying, hey, you're both positively charged, you can't be together. However, the strong nuclear force comes in and it overrides that electric force, and it says, sorry, for any semblance of life to exist, we have to have these protons stay together. And so that's where the strong nuclear force comes in. It overcomes the forces of repulsion. And then the weak nuclear force is an attractive force that acts only over a short range, and it acts about 10 to the negative 18 meters, less than the range of the strong nuclear force. So it's just kind of like a backup there to make sure that and everything is still being held together. So those are the first three. So we talked about the electromagnetic force, the strong nuclear force, and the weak nuclear force. So we're going to finish off with Newton's view on gravitational force in our next video, and that will be our last video actually of chapter 12. So that's it for this one. Let me know if you have any questions.